Okay, and we're officially recording now, we're live. So welcome everybody to the webinar, Discover the Space Awareness Activities for Your Classroom. My name is Teodora Ioan, and I am a member of the Space Awareness team at European Schoolnet. I will be moderating the session today. With me now is Markus Nielbock. Markus, I hope I pronounced your name right.
Absolutely fine.
Perfect, great. Markus here is a scientist in the Space Awareness Project with a very fascinating scientific background. I think he'll tell you a bit about that. And Markus, today in the session, will address the latest developments regarding the teaching resources we're developing in the framework of the space awareness topics. And this is Our Fragile Planet and Navigation Through the Ages. These new materials focus on currently the most relevant topics of climate change, featuring a prototype that I think Markus will show called the Climate Box, as well as the history of navigation through astronomical tools. So this is just a few sentences regarding our session now. The presentation will last about 45 minutes, and after that we will have around 10-15 minutes for your questions. So during the session, please type your questions in the chat. I will collect them. And by the end of the session, I'll have a list of everything and I will address these questions to Markus. In case you encounter any technical problem during the presentation, please write to me in the chat and I will support you through it. You can find the chat tab on the right side of the screen. Just type your issue there and I will do my best to help you. Okay, if you want to share your question or an idea or a comment, if you want to share it with everyone, when you go to the chat, please select the option Everyone in the recipient menu. And then all of the other participants will be able to see it. And with that being said, I now will leave the floor to Markus. Welcome, Markus. Thank you for being here.
Hello.
And, yeah, enjoy everyone.
Okay. So also welcome from me here from Heidelberg in Germany. I am based within the House of Astronomy here in Germany in Heidelberg, which is an institution for public outreach and education in the field of astronomy. So as you have heard today, I will try to tell you something about the latest developments that we have made here in the project of space awareness. I hope you will enjoy them. So let's just start off because the time is really limited. So as Theo already told you, I will tell you something about my background, my personal background, because some of the aspects of space awareness is also about space career paths that several people could take, and here's just one example. So I'm from a classical working class background, so academics is very foreign in my family, so I'm the only one basically. I received my PhD in 2001, and since then I worked as an astrophysicist in star formation research in several positions. During my professional time, I was also based with ESO in Santiago, and I worked at the Lucia Observatory in Chile. And later on, I moved to Heidelberg to the MPIA, Max Planck Institute for Astronomy, where I had the pleasure to work for the Herschel Space Telescope. That was really a very interesting experience for myself. And since 2015, not so long ago, I moved over to the Space and Astronomy Education and Outreach business here at the House of Astronomy in Heidelberg. Okay. So before we start off with the materials, I thought it would be a good idea to tell you also something about the background of the project itself, space awareness, because I'm not really sure if everyone is really familiar with it. So it is a European-funded educational program which is linked to European space programs, and it combines many countries in Europe and also some of them in Africa. And the ultimate goal of this is that children and juveniles realize or recognize space as a career opportunity for themselves. How do we do that? Well, it's a multitude of different approaches. There's teacher trainings, online courses. development of new lesson schemes. That is what we have been doing, additional materials, and the best part of it, it's all open use and free of charge. Everything is published under a Creative Commons license, so everyone can just pick the resources and use them at their free will. So, classroom activities, fine. Everything in space awareness is differentiated into several main topics. For the development of the new materials, there were the main topics our Fragile Planet, which is about basically our Earth as a harbor for life, and we have focused a lot of on climate and climate change here. The other big topic is the navigation through the ages, which basically deals with the history of navigation and celestial navigation, basically in all the tools up to modern technologies. And there's a third part that we have been working here on, which is called the Journey of Ideas, which deals with the evolution of astronomy from ancient to modern times, and also the journey of the ideas from the Lower East to Europe, back and forth. But this is basic. This is nothing I will not tell you anything about that, because that was developed by a colleague of mine. So we concentrate on these two topics today. So what's the general design of these new activities? Yes, we have made our minds up, and everything began within the project with a very thorough analysis of international school curricula, so that we know what are the connections between what is taught in school and what we could provide with the new developments. And all these activities, they are supported by suggestions for discussions, question and answers, so how you can actually embed these activities and the new resources within your lessons, the lessons of the teachers. Everything comes with up-to-date background information, also with sources, so where you can try to do your own research if you want to. I just skip a few points here, but it is basically also suitable for adoption by many countries, which is a very important point here, because we want to reach out also to underprivileged communities. In the end, that's the goal. Everything will be translated into at least 8 languages, and all the new and also already existing researched resources will be reviewed in a peer review process via this AstroEdu portal. I just received recently the comments for all of these activities, so it will take me a little bit of time to work this all in, but yes, the work is ongoing. Right now we have the prototypes available for everyone. We publish them on our project website. You will have the opportunity to see the link at the end of this talk. And yes, you see here that all the new developments are basically done for secondary schools, but there are also primary schools activities available. We have done an extensive research before the new developments, where also primary school activities were included. And they are also shared on our project website. So, Fragile Planet, quickly. Why do we call it Fragile Planet? That is perhaps a question you might have, because when you think about Earth, it has been around for 4.5 billion years or so, and it could be considered as something very constant and rigid and hard to disturb, basically. But this view basically changed a lot, at least when the astronauts first saw the Earth from outer space. So this is in a very famous image taken by the Apollo 8 crew from an orbit around the moon. And here it's obvious that the Earth is something, that is surrounded by vast empty space within a hostile environment, and it's almost a miracle that actually life is existing on that planet, and it's something very precious that we have to maintain. So that's the basic idea. And right now we're facing many challenges. You can just pick the one that you like most, but what we've done here is that we concentrated, focused on climate change. All the other aspects are of course related to that. And now that we are populating the Earth and we are changing it for good, and with a lot of lot of consequences. There are some scientists even say that we might have advanced into a new epoch, a new era that they call the Anthropocene, where mankind is the dominating factor that changes the surface of the Earth. In order to get a hold on what is actually happening on Earth, several countries and institutions have started huge monitoring programs, basically from space. And also Europe has done that. There's a program that is called Copernicus. This is ongoing. The first few satellites are already in orbit, and they have a multitude of applications, and they can do a lot of different things. They observe the atmosphere, they can analyze the content of the atmosphere, they can measure altitude differences on the surface of the Earth, many different things. And this entire program, at least this topic, our fragile planet, is closely connected to this Earth observing program. And here are a few key points, keywords that list some ideas where and at what point the different topics within these new developments of school materials can connect to school curricula. Where actually, so these are the keywords that have been researched by our colleagues within the project, and these are the links basically, and this is were the basis of the new developments. Okay. So then we came up with the idea that perhaps we make it into a big, this climate aspect and the new developments, we make it into a coherent toolbox. This is something that we have been doing at the House of Astronomy for different physical topics already. And so the idea was to put everything within the case, a briefcase. Everything should fit inside. All the materials should be easy to get, so nothing very fancy, nothing very expensive, so that at least the majority of all the schools that want to use these resources can actually get those materials that are needed for the activities by themselves quite easily and for very low prices. Up to now, we have 15 new resources that deal with weather, climate, and climate change. And as I said, at the moment, they are prototypes, but already in a very good shape, so they can be used already, right? And I do not expect any big changes to them. So this is what it looks like. I also have it with me here, so I will show you later on an example with that. But I want to tell you something about the big picture, so the vision that we had, how to actually set up this entire toolbox. So it goes along a golden thread, where we start with the Earth itself, a unique planet that hosts life, the only planet that we know of that actually hosts life. So that means general topics might be something like the habitable zone within the solar system, and also the extrasolar planets with their own. There's a feedback somewhere. Can please everybody else mute your microphone? Thank you. So like also the habitable zones and exoplanet systems. Then we use the sun as the main energy source for the Earth, and how that interacts with the Earth's surface, for example, and how the entire engine of weather and climate actually is fueled. This leads us then later to weather and climate. So we start with weather phenomena, and then later on we try to explain or describe the link to actually what is the climate. So, and from that, we then go on to climate change. What can we measure? What is the evidence of climate change? There are several. What is the evidence of actually what is the human contribution to climate change? And so on and so on. And then the final chapter would be that, some ideas how we can actually turn around the development that we face right now, or actually mitigate, so reduce the effect on a global climate system. This is something perhaps then even for the future, because for that topic, we haven't developed anything at the moment, unfortunately. There was no time. To get into the specifics, I just picked one of the activities that we have developed, which is called Oceans on the Rise. You can already imagine that this is about the rise of the sea levels. So this is the experimental setup. I have it with me here, so I just, if you would like to enlarge the camera view now, because I turn around to the experimental setup right here in this room. So what we have here, so that should be it. Okay.
Sorry to interrupt, Markus, just a second for our viewers. If you want to enlarge the camera view, just hover over the camera, and in the top corner on the right side of the screen, you will see 2 arrows there. So if you click that, you'll be able to enlarge the camera. And then if you click escape, you can go out again. That's it.
Okay.
Thank you.
So, all right. So what we basically have here, this is really part already of this climate box. These are some of the parts of this climate box. So we have this little bottle. This is filled with water, just normal water from the tap. And in here, we have a glass tube. And you can see here that there's a certain water level already within the tube. Okay? And I will mark that position for later so that we can actually see if there has been any change later on. And in the background, you see a very strong lamp. I will turn that on now. So very bright. And in order not to warm up the water in this tiny tube, glass tube, I block it with some material so that only the water inside the bottle is heated. So what is going to happen now is the water will heat up, and due to the normal expansion of liquids, and also gases do that when they're heated up, the volume of the water will increase, and by that the water level within the glass tube will rise. We will see that later. Maybe I can just show you right now where the level is. I hope you can see that. Is that possible? Can you see the marking? Is that possible? Okay. So I return now to the presentation, and later on we will see what happened with the glass tube. Okay. So that's the experimental setup for that activity. It's quite simple. Now I have to get back to here. So what do we need for that? You've seen that. There's this flask, this little bottle. There's a rubber stopper with a hole, the glass tube with a small diameter. In that case, it's 4 millimeters. And you can also employ a thermometer. I skipped that for this presentation because what you could do actually is measure the temperature of the water in the beginning, and then afterwards, after the water level has risen. Okay, and I thought that maybe a good age range for this activity is something between 10 and 14-year-old students. So before we actually get to the results of that, I would like to tell you something about the background. But I was also asked for some of the participants of this webinar to maybe highlight or come up with some ideas that are somehow not STEM related. So what I came up with is basically, for example, politics, because all the climate change topic, of course, relates to international treaties and some political issues between the so-called first and so-called third world. Of course, sociology is an important aspect, because if everything is going to get worse, then we should expect refugees due to flooding and other consequences. And of course, there's economy involved, because everything will come with a cost. So what is the evidence for actually the change of the climate and the sea level rise that we witness right now? So this is a very important graph, because what you see here So this is all part of the materials, part of the resources that you can download. This is part of the background information for teachers. So what you see here are basically two curves that show a development that goes back 800,000 years ago. So it's from minus 800,000 years up to the present. And what you see here is the blue curve. It has different shades. It really doesn't matter what it means, but it just tells you the amount of carbon dioxide in the atmosphere throughout history. And the red curve tells you shows you the change of temperature in the same time range. And you can see that, yeah, it goes up and down, and what also obvious is that the level of carbon dioxide within the atmosphere is always very closely related with the temperature. And actually, what is indicated here as current CO2 level is already outdated. Right now, we are here. And it's increasing more and more every year. So here are some nice aspects, because all this is based on ice core samples taken in Antarctica. And maybe it would be also nice to learn a little bit about what it's about living and working there, because it's a very remote place, so it touches psychology and sociology. And also the legal status of Antarctica is not really clear, because there are some countries that actually claim huge parts of this southern continent. So it touches politics, economy, and the law. So when we talk about climate change, everybody's thinking about warming up the atmosphere. Yes, this is a dramatic change that we see. Right now, we are already about 1.5 degrees above pre-industrial level. But when you take a look at where actually all the warming is going into, the atmosphere itself on a global scale plays a relatively small role. Most of the warming goes into the oceans. Yeah, because one aspect, of course, the most of the surface of the Earth is water, is oceans, but also it's a physical process which is related to what we call the heat capacity, because water can much more store heat much more efficiently than actually air can do. So if we do not understand what's happening in the oceans, we do not understand climate change at all. So it's a very important aspect. And what you would expect is, if the oceans are heated up, you should, or when the energy is going into the oceans, you should expect that the water should heat up. And this is also what we see. So not only the atmosphere, not only the air is heating up, it's also the water in the oceans. So this is a graph that shows you the temperature, how it changed throughout history from pre-industrial times until the present. And so now we can ask ourselves what happens with gases and liquids when they are heated up. I mentioned that already, they expand. So what we should expect is that simply, it's not really only what everybody's thinking about, yeah, it's melting the ice caps and so on, and this adds a lot of water to the oceans. It's just simply heating up the oceans that actually contributes to the rise of the sea levels. And this is also something that can be measured. This graph here shows you, this is the blue line, in time, the component just by heating, by how much the sea levels have risen already. And when you take the entire curve, it's something like 4 centimeters, just by heating up due to the climate change. And this is a contribution that amounts to about 1/6 of the total sea level rise. It's a small contribution, but not negligible. Okay, so when you now do this activity with the students, then of course you can try to tell them something about the backgrounds. Depending on the age, they might already have some background information, some knowledge about it, and then just approaching this experiment. Of course, they should tell you what they observe. This is a very important part of the scientific process of experiments and gathering knowledge. Simply first exactly describe what you observe. In this case, it's something like, you see that water is irradiated with a strong lamp, and in the end, we see that in a moment, the water level rises. Then the next question, of course, is why did the water rise? What's the reason? And then they should come up with an answer like, okay, yes, the water is heated up because the lamp irradiates the water. And by that, we expect that the volume of the water expands and also the water level rises. And then you get to the transition to nature, to the actual situation on Earth. So you can ask, for example, what does this mean for the oceans? And then the transition is very simple, because when they know that most of the heat goes into the oceans, they should immediately come the answer, yes, they should rise as well. Okay, let's have a look. This was just a few minutes. If we see any change. So when you go back to the video, if you want, but I can also, for those who cannot do that, I can just tell you what you should see. Maybe you can you see something here? Yeah. So what you should see is that within these few minutes, the water level has risen already by something like 1 centimeter. And I have made this experiment several times for myself, so you should expect something like 1 centimeter every 10 minutes or so. Okay, so I switch that off again because it's very bright. Okay, so that's one example how to include the newly developed resources into the school. Then you can take it a little bit further. Now, this could be done with very young pupils, with very young students, it's just observing the thing. But then for higher grades, you can do even some very simple math, because you can try to calculate by how much actually does water expand. And it's not very expensive. It's not very. Somebody cannot hear it. Can you help? Okay. Should I continue or just wait? Okay. So we came up with 2 exercises for very simple calculations. The first one is just calculating by how much a liter of water would expand when you heat it from 10 to 20 degrees. And the second exercise is a little bit more realistic. Here we assume a much bigger volume. Imagine you have an ocean depth of 3,800 meters. This is something like the mean value over all the oceans. And you imagine that this is a column with a base area of 1 square meter, and then you have a volume with which you can work, and you try to calculate the heating from 4 to 5 degrees Celsius. I will come to that now, because this is the very simple basic principle, because basically everybody knows who already knows something about what density actually is, what it means, that it's just the mass divided by the volume. So how much mass fits into a certain volume. That's the density. So, and now, in this example, which of those quantities stays constant? So it's very simple, because we do not add any water, we do not remove any water. So that means the mass, the total mass, does not change. This is a constant in the climate system, more or less, at least within this simple exercise. So that means the product of the density times the volume is also a constant. So the mass stays constant. It means if you have an initial condition of a density and a volume, and you multiply that, any other condition that this system attains has the same value. And that means you can simply calculate, if you know what the density is, you can simply calculate the volume change. And with the materials, we provide a table with the numbers. So you see for each temperature in Celsius, you see what the density of normal water is. You just put it into the equation, and then you get something very, very little. So it's just an increase from 10 to 20 degrees by 0.15%. That's tiny. And you should think, does it matter globally? Is it really so much? Cannot be. At that point, I have also to tell you that these values, of course, the densities are only for fresh water. Salt water has different densities. They're a little bit higher than that, and seawater also reacts a little more strongly to temperature changes. If you want, there's a link where you can actually calculate these values for different temperatures. But for this kind of exercise, fresh water is absolutely fine. So you can continue with the second exercise, which is more realistic. I already mentioned the numbers. You do exactly the same calculations with the new numbers. This time it's the product between the density and the volume at 4 and 5 degrees. You solve the equation for the volume for 5 degrees, and then what do you get? So the initial volume for at 4 degrees, that's the starting position, is 3,800 cubic meters, because you have a column of 3,800 meters and a base area of 1 square meter. That's simple math. So and then you put it in, use the table before, and what you get is this. So in the end, you get a rise of almost 8 centimeters. And this is a very realistic value that we have seen already with the actual measurements that have been done. So what you see here from this very, very simple and simple calculations is, first of all, what the students can learn from that small effects can have really huge impact. It's just the sheer amount of water that actually changes the whole situation from 0.15% to actually something that is very easily measurable. And the other thing is, climate is not very complicated if you just look at the basic principles. Yes, it's a complex system, and it's very difficult to actually disentangle everything. But if you only look at the basic principles, this can be easily understood with very simple school knowledge. So, and here I came up with some other STEM-related issues, like maybe this is very up to date, because psychology and media, about you can maybe use that as an example for denial of obvious facts. And of course, for economy, you can perhaps say something about the cost of repair versus the cost of prevention. So what is cheaper, what is more expensive? Maybe that is something that could be done. Maybe I can just quickly answer this question that came up. Why does water expand? Temperature is a measure of movement. So when the temperature rises, the molecules of the water, they move faster. The individual velocity increases. This means they hit each other much more strongly, and this leads to a volume increase, because when they hit each other, they need just more space, they need more room to actually do these interactions. So it's a microscopic explanation. I hope this helps. Okay, that was about climate change. I hope I am not extending the time. Yeah. So I would now try to get to the navigation part. This is also linked to a space program. So this is also quite interesting, because Europe now has its own navigation satellite system. Everybody knows GPS, the American thing, but also Europe is building up on its own. I'm not going into detail, because that would take too much time. You can just try to dig up the information by yourselves. But maybe one interesting aspect is that the initial services are actually starting today. So everybody who has a receiver that can work with the Galileo information coming from the satellites, it's already working now. But unfortunately, there are not many available at the moment. Yes, and since this is a really big treaty, Galileo is a big treaty with lots of different countries involved. Also, the US had some say about what is actually happening within the satellite system. So politics and international law might be something that could be interesting within that respect. So what is the link to the curricula? That's also quite obvious. So it's not only, of course, now the Galileo program, it's just navigation as a whole. So we have the cardinal directions, north, south, west, east, for example. Then we have coordinate systems, celestial navigation, instruments, and so on and so on. And these keywords that can be easily found in any school curriculum for certain ages. All right, so the activities. For this part, there are not so many when it comes to new developments. Right now there are 5, but I'm planning on extending the number a little bit further here. We're touching 4 historical epochs at least, and each of the activities, the descriptions or the resources that you download, they come with extensive bibliographies for your own research, and they all come with, again, with some comprehensive background information that links history to navigation and their tools. So everything is very much connected here. And how is this all introduced as activity?
Strong word, drafting, calculations, so it's really a good mixture. Okay, what are the historical epochs that we actually use right now, that we chose? Well, it goes back to ancient history, that's basically Bronze Age, some aspects, like even going a little bit more farther to into the past. Then we go to the Middle Ages. There are some interesting aspects. There have been new developments being made. So in the ancient history, it's more qualitative. In the Middle Ages, it's more about measuring, exact measuring. And then later on, we come to the age of exploration. Suddenly, the entire Earth is being explored. Seafaring becomes very, very important. And then new tools and new skills had to be developed. And then finally, we come to the modern times. Right now, this is about satellite navigation system. There's one resource, one material that is dealing with that topic. And there's a very obvious list of non-STEM related issues like history, literature, and ancient languages. So for this purpose here, for this talk, I picked one activity that I coined the navigation in the ancient Mediterranean and beyond. I only can touch a few aspects of the entire activity, the entire document you can download. Here it's all about cardinal directions, so that means where are we looking at, so north, south, east, west, or basically just pinpointing directions, headings for navigation. So of course you cannot, if you do not have any tool with you, you can use celestial objects like the sun, the diurnal movement of the sun, to indicate, to derive the cardinal directions, because everybody knows in the northern hemisphere the sun attains its highest point towards the south, in the southern hemisphere is the north, west, and rising and setting of the sun is more or less, it changes a little bit throughout the years, more or less east and west. Yes, this is already something where celestial objects can be used for that. But what do you do during the night? Then, of course, you can use the stars. And Bronze Age navigators, they were already much more sophisticated than that, just deriving these cardinal directions. They could do it even better than this. And for that, we have to understand the following thing. So this is a view from Heidelberg to the east, not very long ago in November. So you see the constellation of Orion, half of it, and you may also see the star Rigel right at the horizon. So this is a view towards the sky, roughly towards the eastern direction. So just try to recognize, or just try to remember for the next picture where Rigel is standing. So what I do now, I show you the same picture for half a year later. And you see, it doesn't change. And the consequence out of that is, so that the positions, the rising positions of stars and constellations, they do not change throughout the year. It's always the same position along the horizon. So what we call the azimuth, which is the angular direction along the horizon where we can look at. Yes, it changes a little bit, but only within millennia. It's a very long-term process, but within years, few years, these positions do not change. And these navigators knew that, and they used it. So they could use it, and they knew where certain stars rose at the horizon and used that as a direction indicator. And later generations, they made it even more sophisticated. This is something that actually really existed. This is what is called a stellar compass. So it's basically a disk. And with lines or markings at the edge of the disk, and all these markings, they indicate the azimuth direction, the direction towards the horizon for certain stars. This was all documented, and it's very well known. So this is really fantastic, I think. No? This is really something one can think about a lot. So what's now the connection to the old ages? The connection is very clear, rather clear, because there has been a civilization in the Bronze Age that's around 2nd millennium before Common Era. Those were the Minoans on the island of Crete, now Greece. And of course, the idea that, or the imagination that many people have, that the early navigators, at least in the Mediterranean Sea, they oriented themselves along coastlines. Yeah? Coastlines, this is easy so that they do not get lost. And this is what they did, of course, in the first millennia of seafaring within the Mediterranean. But for the Minoans of Crete, that was not an option, because it's an island, and they had ties and relations to different cultures and civilizations throughout the Mediterranean. The closest is the northern Aegean Sea, which is 60 nautical miles away, with a standard sailing speed of, let's say, 5 knots. That would take them half a day. And within half a day, you lose the sight to the island. Another example is Sicily. It's 200 nautical miles, and they had trade relations to Egypt, 290 nautical miles. So they had to have some knowledge, some tools, how to actually navigate across open sea. No? And there's a lot of evidence that indicates or suggests that these Minoans actually used this kind of knowledge that stars rise and set always at the same direction towards the horizon. There are several indications that also come from literature. For example, the Odyssey by Homer. There's a clear mentioning of navigational instructions, and scientists think that those instructions actually date back to the Bronze Age. There's also an interesting part of literature by the poet Aratus of Soli, also a Greek person from the late Bronze Age. In his work, Phenomena, he provides a list of stars and their rising directions in the order of the rise throughout the day. And when you use these numbers and calculate for what age these numbers actually, or to what age they point, because these rising directions, they change within millennia. This is not actually the time when Aratus or Solar actually lived. It's basically the Bronze Age. So it's quite clear that Bronze Age civilizations knew about this phenomenon, that the stars always rise at the same position, and this could be used as navigation tools. And here's an indication how they might have been doing it. We know that the Polynesians have been doing this. Polynesians, they even have a much, much older history in seafaring and navigation. But what they could use is certain parts of their boats and their ships as indicators, and then orient themselves with these parts of the ships towards the sky, and use then the constellation and the stars to keep a certain heading towards a direction that they actually would steer to. All right, so what's the activity for the students? That's very simple. They should just build their own stellar compass. And this comes with of course, again, with worksheets, with some instructions how to do that. This is the list of items that they need. And so this is the blank disk. And in the end, what they should do is calculate the positions of stars that are provided to them. I will show you in a second what those stars are. And they locate them at the edge of the disk. So that's just one example for something they could do. And the best part is, if they just use their own latitude, where they're based at home, you can actually check if this stellar compass actually works. Right? So what I can try now is, let's see if that works. quickly. So here's an Excel spreadsheet. And this spreadsheet actually lists 57 selected navigational stars that are being used currently in modern times for navigation. And so you have the common name, another designation, the azimuth of rise, the azimuth of setting. And then at the bottom, you have 2 rows where you just indicate at what elevation you would like to observe the stars. The good value is 10 degrees above the horizon. 0 degrees would not be very useful because then there are lots of things that can block your view to the horizon. So 10 degrees would be nice. And then you could use put in your own latitude. Here is another example of 50 degrees north, but you could also put in 10 degrees north, whatever you like. And then the spreadsheet automatically calculates the azimuth for each of those stars. And the students can just take these numbers and then add them to this stellar compass. So that's the idea behind that. So everything again is also supported by introductory videos. There are some nice documentaries that can be used and shown during class, and there are also some examples and suggestions for question and answers, how to flank actually this activity. And there's some additional background provided with these resources about Bronze Age trade, which triggered actually seafaring and new developments in navigation. And there's also an interesting story about Pythias, a Greek scientist of the Bronze Age, who was the first Greek who actually left the Mediterranean, found the British Islands, and then even made it farther north, and people think that he might have even been to Iceland because he talks about ice on the water. And he has made a lot of very interesting measurements, a very interesting figure in history. Okay, so this is basically now the other example I wanted to tell you about. There's much more with very different approaches, with very different activities. And if you would like to have a look for yourself, this is the link to our website, the project website. And right now we also published a call for testing because we want to know what you think about resources. And if you would like to participate in testing resources during your classes, then you're free to do that. But before that, it would be good to contact your local dissemination point of our project, and they will help you with what to do with it. Okay, so that leaves me with the final words. So these were the few examples, and I end here with my presentation. Thank you very much.
Thank you, Markus. Very nice presentation. And now we have some time for a few questions. I saw someone already posted a question. I think you managed to answer during your presentation. And then the same person was asking if you suggest the microscopic
somehow I cannot hear you, Theo.
That's weird because I'm talking. I see the microphone is working. Can anyone else hear me?
Warning message with audio.
Okay. It seems other participants are hearing me. Okay, just a second, everyone. We're trying to figure it out. So let's see.
But can you still hear me? Okay, I cannot hear you, unfortunately. Very strange.
Okay, everyone. Then what I propose is, so I will talk live, so you can all hear me, and at the same time, I will address the questions to Markus in the chat. So I'll just write this to him.
Yep. Okay. Fine.
Okay. So as I was saying, there was someone who was asking if Markus suggests the microscopic explanation for primary school, or is it too advanced for students 6 to 12 years old? So I've sent Markus the question. I told him to speak up, so let's see what he says.
Well, just explaining it that way. Just explaining it that way with the microscopic approach might probably not be very much suitable for primary school children. But there are very simple ways to visualize it. Because, for example, what you could do is, I don't know, have a container, a small container with styro balls, or maybe a larger container with table tennis balls, and you just start shaking them, and then tell them this is what actually temperature is about. And when you start shaking them much more strongly, you will see that some of them jump around and even are kicked out of the container, and that immediately, I would say, would give a nice impression of volume increase. I think that might be an explanation. So visualizing it might help in that case, I guess.
Thank you, Markus, for that answer. If anyone has any other questions for Markus, now it's the time. We have 5 more minutes, so please write them in the chat. And I will address them.
I just recognized that probably my headphones switched off, but I can barely hear you through the loudspeakers of the laptop that I'm sitting at.
Okay, so I don't see any other questions being posted.
Okay.
Let's give it 1 more minute.
Yeah.
Also, if anyone has, go ahead, Markus.
I can suggest that if you have some additional questions later on in the next days or so, if you want to just experiment a little bit with the resources and then come up with some questions, of course you can contact me. That's a simple approach. I'm very happy to answer any questions. Just write an email. Yeah, thank you.
Yeah, I think only Santa can answer that one. But in any case, as Markus said, if you want to try the resources, please go ahead. We will also have, building on what Markus was saying regarding to navigation for the ages, during the next Space Awareness MOOC that will be launched end of February, we will work a lot with the resources that Markus was talking about. So if you want to try out, the resources before then and come up with some questions, I think it will be quite interesting for you if you decide to participate after that in the course. Okay, I think there are no more questions. Then, Markus, thank you again so much for taking the time to present all of this. It was a very great presentation and very useful resources.
Thank you. It was a pleasure for me.
Thank you, Markus. I've posted the link to the website where everyone can find the resources Markus has mentioned. After this, we will post the recording on the Career Hub of the project. I will also send a follow-up email to everyone, also with the link to a survey where you can give us your feedback. And also, short heads up, in February, we will have the next webinar with on the topic of lunar exploration. So keep posted, follow us on social media, and you'll find out more about the next session. Interesting tip, you will be able to participate with your students in this session. So I hope that's an exciting idea for everyone here. Okay, thank you, Marcus. Have a nice evening, everyone. And we'll be in touch shortly. Take care.
Okay, bye-bye. Thank you for attending.